A-level mock exam. Question 1. This question involves the use of kinetic data to deduce the order of reaction and calculate a rate value for the rate constant. The data in Table 1 were obtained in a series of experiments on the rate of reaction between compounds A and B at constant temperature. Show how these data can be used to deduce the rate expression for the reaction between A and B. So the key thing about this question is the fact that we've got to show how these data can be used. So I'm going to look at the table to start with. And if we look at experiment 1 and 2, we can see that the concentration of B remains constant. A concentration of A between experiment 1 and 2 goes up by a factor of 3, and the rate goes up by a factor of 9. So we can deduce from that that the order with respect to A is first order, but we've got to put that into words. Now let's consider experiments 2 and experiment 3. So between experiment 2 and experiment 3, the concentration of A has doubled. So we'd expect the rate to go up by a factor of 4. In fact, the rate has only gone up by a factor of 2. So B must be having the effect of halving the rate. If we have a look, it's gone down by 2. So therefore, if it's halved the expected rate, and it's halved its concentration, then it must be first order. Again, we've got to put that into writing. Finally, we need to make sure we deduce the rate equation expression. So that is going to be rate is equal to K times the concentration of A squared as its second order, and times the concentration of B. We don't need to put a number in because that one's first order. In terms of the scoring, we get 1 mark for successfully explaining that bit, another mark there, and a mark for the rate equation. If you had put numbers in on the table at the top, that may have been interpreted by the examiner as explaining how you worked out the rate with respect to the concentrations of A and B. Be careful. Some people for some reason said multiplied by 2 there, where it's clearly being halved. The data in Table 2 were obtained in 2 experiments on the rate of reaction between compounds C and D at a constant temperature. Experiment 4 and 5, the data is given in the table. The rate equation for this reaction is shown below. Use the data from experiment 4 to calculate a value for the rate constant K at this temperature and deduce the units of K. Right, so we know that rate is equal to K times the concentration of C squared times the concentration of D. Therefore, K is going to be equal to the rate divided by the concentration of C squared times the concentration of D. And you get 1 mark for correctly showing that equation. We then just need to substitute the numbers in from experiment 4. So we've got 7.2 times 10 to the minus 4 divided by 1.9 times 10 to the minus 2. Obviously that one's got to be squared, multiplied by 3.5 times 10 to the minus 2. That gives us a value of 57. The numbers in the question have been given to you in to 2 significant figures, so it's perfectly acceptable to put this answer to 2 significant figures. For some reason, the mark scheme shows it to 3, but there is nothing about significant figures. I would argue you should only have that 1 to 2 though, because that's all the information's been given to you in. Okay, we then need to work out the units. So if we have a look at the units for K, we've got moles dm to the minus 3 seconds to the minus 1 on top. We've then got moles per decimetre cubed squared times moles per decimetre cubed. If we simplify that, we end up with seconds to the minus 1 over moles squared dm to the minus 6. If we bring that up onto one line, we end up with moles to the minus 2, dm to the plus 6, seconds to the minus 1. It's always worth helping the examiner. So if there's space for the answers, it's worth putting them in again where they've asked you. A happy examiner is more likely to be generous. For 1.3, we're trying to work out the rate for 5. Now we have the rate constant, we can just substitute the other numbers in. Now this question was consequential on you getting the correct, on using your value of k. So if you got your value of k wrong, but you used it correctly in this question, then you would still score the mark. That should be 3.6 times 10 to the minus 2 squared, multiplied by 5.4 times 10 to the minus 2. Okay, again, the mark scheme gives the answer to 3 significant figures. I'd argue you've only got 2 significant figures in the information, but so I certainly would have accepted 4.0 as an answer to that question. If you want to put units in, it's optional, but they are the units for rate, which is mol dm to the minus 3, seconds to the minus 1. So moles per decimeter cubed per second. Again, I would pander to the examiner, and I would be tempted to say put your answer in the space that they provide. If you do copy it, make sure you copy it correctly. A few people copied it without putting the times 10 to the minus 3, which is just daft and will lose you the mark. So the rate equation for a reaction is rate equals K times the concentration of E. Explain qualitatively, so we've not got to go into numbers, it's quite a basic explanation, why doubling the temperature has a much greater effect on the rate of the reaction than doubling the concentration of E. Going back to collision theory, that might be something that you need to revise. So you've got to remember that a reaction will only occur if the particles collide with energy equal or greater than the activation energy. And there's a shorthand way we can do that, so we can say their energy is greater or equal to the activation energy, and that shorthand is absolutely fine to use in an exam. So if we double the temperature, we're going to cause many more molecules in that sample to have energy that is greater than the activation energy. So a larger percentage, by a long way, are going to have the sufficient energy to react. Whereas if we double the concentration, the same percentage of molecules that had activation energy in the original one would have that in the double, it would be the same percentage in the double concentration. So it's going to have less of an effect. So increasing the temperature is always going to have a greater effect than changing the concentration. So let's put that into words. A slow reaction has the rate constant K equals 6.51 times 10 to the minus 3 moles to the minus 1 decimeters cubed at 300 Kelvin. Use the equation to calculate a value in kilojoules per mole, so that's going to be important. We need to make sure we've got the right units at the end. For the activation energy of this reaction. We've got the constant A and we've got the gas constant there as well. Right, so we've been given an already simplified version of the Arrhenius equation, which makes life a little bit easier. So we know that log K equals log A minus EA over RT, and we're trying to work out the activation energy. So we need to rearrange this equation to work out EA. So we're going to end up with log A minus log K, and that's got to be multiplied by RT. You can rearrange it in as many steps as you like. Right, so if we substitute the numbers in, we know that we've got to do log of A, which is 2.57 times 10 to the 10, minus log of K. K is 6.51 times 10 to the minus 3, and then we're going to multiply that by RT. R is 8.31 and T is in Kelvin, and it's 300. Okay, so that gives me an answer of 72307. Now I need to check what units I've got that in. So if we go back to the original one, we know that's in Kelvin, that's in moles per decimeter cubed, that's in moles, that's fine. That's in Kelvin, but that is in joules. Everything else is going to cancel out, leaving that in joules per mole. Now it specifically says in the question that we need it to be in kilojoules per mole. So if you divide it by a factor of 1,000, that will convert it into kilojoules per mole. So that's the same as 72.3 kilojoules per mole. We've got to choose suitable precision for the answer. So if we have a look, that's to 3 significant figures, that's 3 significant figures, that and that are 3 significant figures. So putting our answer to 3 significant figures is reasonable. And again, make the examiner's life easy, write it where they want the final answer. So it's worth 2 marks. You got 1 mark for correctly rearranging the equation. Now in the mark scheme, that has the factor of 1,000 in that equation. But as long as you work it out and show your units, it doesn't matter whether you do it there or at the end. And then you get 1 mark for the answer. The acid dissociation constant Ka for ethanoic acid is given by the expression shown below. The value of Ka for ethanoic acid is given at 25 degrees C. A buffer solution is prepared using ethanoic acid and sodium ethanoate. In the buffer solution, the concentration of ethanoic acid is 0.186 and the concentration of sodium ethanoate is 0.105. Calculate the pH of this buffer and give your answer to 2 decimal places, so that's going to be really important. Right, so the first thing we need to do is rearrange the equation to work out H+. Okay, now you've got to remember, if it's a buffer question, that is the original acid concentration, because we say that it's barely dissociated, so we don't worry about any change, and that is the salt concentration, because there's going to be a huge excess from the salt of the A- ion, or in this case the CH3COO- ion, so any other contribution to that from the acid is going to be negligible. So if we substitute the numbers in, then we get a hydrogen ion concentration of 3.08 times 10 to the minus 5. We're going to get 1 mark for rearranging and 1 mark for working out the hydrogen ion concentration, but that's not quite the end. It's asking us for the pH. It's always worth writing in the equation you're using. Then if you make a mistake, there might be some credit for having the right equation. So if we do minus log to the base 10 of the hydrogen ion concentration, we end up with a pH of 4.51. Remember, the question said to 2 decimal places, and unless otherwise stated, pH should always be displayed to 2 decimal places. In a different buffer solution, the concentration of ethanoic acid is 0.251 moles per decimeter cubed, and the concentration of the sodium ethanoate is 0.140 moles per decimeter cubed. A sample of hydrochloric acid containing 0.015 moles of HCl is added to a decimeter cubed, makes it very easy, of this buffer solution. Calculate the pH of the buffer solution after the hydrochloric acid has been added. You should ignore any change in the total volume, so we can assume it stays at a decimeter, and give your answer to 2 decimal places. So we've got the concentration of the salt and we've got the concentration of the acid, so we could work out the original concentration of the buffer really easily. But when we add HCl, we're going to change the moles of ethanoic acid and the moles of salt. So we're going to need to recalculate those concentrations. So let's have a look what happens. If I add H+ ions, it's going to mop up some of the A- and it's going to make HA. Just get rid of that. Shouldn't have put a curly bracket there. That means concentration. We're not talking about concentration at the moment. Okay, so it's going to make HA. So what we're going to find is that the concentration of the acid is going to go up because we're making some, and the concentration of the salt is going to go down. By how much is by the number of moles of acid added. So let's work out the original moles of each and then how many are going to have been used up or how many are going to be added. This is one of the reasons they've given you a decimeter exactly, because it means that when we work out our moles, it's going to be the same as the concentration. So I can do the same for the moles of A minus, and that's just going to be 0.140. Okay, we said the moles of HA are going to go up, so that's going to be 0.251 plus 0.015, which gives me a total of 0.266. For this one, it's going to go down, so it's going to be 0.410 minus 0.015. You can see how valuable this little thinking bit at the top was, because it really makes it obvious which way things are going to go, and you're less likely to make a mistake than when you're doing the calculation. Okay, so we've now got the new moles. We need to convert those into concentrations, but as it's in a decimeter, the moles are going to equal the concentration. I'm just going to put that at the top so we're not confused. Normally, you would have to show you were looking at the concentration. Okay, so I now need to work out my new hydrogen ion concentration. So it's going to be Ka, which is still the same. It's not given us another value, so we can assume Ka is going to be identical. So it's 1.74 times 10 to the minus 5 times HA. I might be tempted to show the examiner that I'm turning it into a volume, into a concentration. And it shows an appreciation that you're not just putting moles straight in. Okay, that gives me a value of 3.70 times 10 to the minus 5. There is space on the next page, but I'm going to finish it off on this page so you can see it. Obviously, I now need to convert that hydrogen ion concentration into a pH. And that gives me a pH of 4.43. Again, 2 decimal places. Okay, this particular question is worth 5 marks. Okay, you can see how I've awarded those marks. So these original moles, you'd only get 1 mark for both of those. You then get a mark each for adjusting those correctly. You then get a mark here for working out the hydrogen ion concentration, and finally a mark for working out the pH. Isooctane is the common name for the branched-chained hydrocarbon that burns smoothly in car engines. The skeletal formula of isooctane is shown in figure 2. Give the IUPAC name for isooctane. So the first thing we need to do is identify the longest continuous chain. So that's going to be our longest continuous chain, which has 1, 2, 3, 4, 5 carbons in it. So we know it's based on pentane. We can then see it's got 1, 2, 3 methyl groups on it. Now, 2 of them are very much closer to this end. So we're going to start our numbering from that end. So that would be carbon 1, carbon 2. So we've got 2 on carbon 2, nothing on carbon 3, and then 1 on carbon 4. So we'll call this 2, 2, 4, because we've got to say where each one is. Try to say there's 3 of them, methyl pentane. Isooctane can be formed together with propene and ethene in a reaction in which the molecule of alkane, in which one molecule of alkane that contains 20 carbons is cracked. Using molecular formulae, write an equation for this reaction. Okay, so we know our original one is an alkane and it's got 20 carbon atoms. Well, the general formula of an alkane is CnH2n plus 2. So if we double that and add 2, it's going to be 42. We also know that we're going to get ethene and propene and our isooctane, which we've got the formula for at the top. So that's the easy bit. Now you've got to make sure it's balanced. And the easiest way to balance it is to have 2 of those and 3 of those. And that should now be balanced. How do the products of the reaction in question 3.3 show that the reaction is an example of thermal cracking? So this is a little bit of learn and churn. You've got to know that thermal cracking gives you mainly alkenes and catalytic cracking gives you aromatics and cycloalkanes. Mainly, you're always going to get a bit of both with each. If you don't know your basic alkane stuff, you're going to have to go back and learn it. Any of this could come up in the exam. So our reason here is mainly alkenes are formed. Okay, deduce the number of monochloroisomers formed by isooctane. Draw the structure of the monochloroisomer that exists as a pair of optical isomers. Right, to do this, we're going to have to go back and look at the structure. Okay, I've redrawn it out because I'd scribbled all over it before and you can't see it. So we now need to see where we could put a chlorine. So I could put one on this carbon, or I could put one on this carbon, but they would be the same. I could put one on this carbon, and I could put one on this carbon. This carbon here already has 4 things. It's got 1, 2, 3, 4, so there's no space for a chlorine. I could put one on here, here, or here, but those would be the same. So in terms of distinct ones, we've got 1, 2, 3, 4. The other question is to see which one would appear as a pair of optical isomers. So again, let's go back to the structure. So if it was this one, it would be no good because it would also have 2 hydrogens on it. If it was this one, it would be no good because it would have 2 CH3s on it, so it's not going to be an optical isomer. This one, that's a possibility because that would have this big group on it, this group, it would have a hydrogen and a chlorine, so this is looking promising. These would be no good because they'd all have 2 hydrogens on them as well. So that means it is this. So we now need to draw that as a structure that's recognisable. Okay, note the question doesn't actually ask you to draw the projections or to show the enantiomers. It just shows the structure that could exist as a pair of optical isomers. And because this has got a chiral centre there, then that could appear as a pair of optical isomers. An isomer of isooctane reacts with chlorine to form only one monochloro compound. Draw the skeletal formula of this monochloro compound. So we want something where all of the hydrogens are in exactly the same situation. So if one of them got swapped for a chlorine, it wouldn't matter which one it was, it would always make the same structure. Now we know we've got 8 carbons. If we have this arrangement to start with, then the chlorine could add onto any of these, but it would always be exactly the same. So we now need to draw the skeletal formula of this monochloro compound. So it doesn't matter which hydrogen you substitute, as long as you substitute one. So that's what the original isomer of isooctane would look like, and then we need to stick a chlorine. So I'm going to stick my chlorine on there. It wouldn't matter where you put it, you could put it on any of those and it would be fine. A sample of a monochlorooctane is obtained from a comet. the chlorine in this monochlorooctane contains the isotopes 35 and 37 Cl in the ratio of 1.5 to 1. Calculate the MR of this monochlorooctane. Okay, so we know the formula is going to be C8, H, it'd be normally double plus 2, but this one's going to be double plus 1, and then a chlorine as well. So double would be 16, 17 Cl. So we can work out the MR of the main bit. So C8, H17 is going to be 113. And then we know the last bit is going to be made up of a combination of these two. So we basically need to find the MR of the chlorine. So it's going to be 1.5 times 35 plus 1 times 37. And then we'd need to divide that by the total abundance, which would be 2.5. So that is 35.8. If we add that to the 113, we get 148.8. And again, the examiner's given us a little spot to write it, so let's make sure we write it in that little spot. MRs are usually to 1 decimal place unless otherwise specified, so make sure you do them to 1 decimal place. Isooctane reacts with an excess of chlorine to form a mixture of chlorinated compounds. One of these compounds contains 24.6% carbon and 2.56% hydrogen by mass. Calculate the molecular formula of this compound. Okay, so we need to find out the percentage of chlorine. So if we take 24.6 and 2.56 away from 100, we get the percentage of chlorine as being 72.84. And you're always going to get a mark for doing that initially. Okay, it then just turns into an empirical formula question. So we've got 24.6 divided by 12. We've got 2.56 divided by 1. And we've got 72.84 divided by 35.5. We now need to turn that into a whole number ratio. So if you divide throughout by the smallest number, which is 2.05, you end up with a 1 to 1.25 to 1 ratio. If we want to convert that into whole numbers, we're going to have to times that 1 by 4 to get it into a whole number. So we times them all by 4. So we end up with C4 H5 Cl4. Okay, and that's our empirical formula. But we know this is isooctane, so we know that it's going to have 8 carbons. So the molecular formula must be C8 H10 Cl8. It's a little bit trickier perhaps to get the last mark on that one. Alcohol A undergoes reactions separately with acidified potassium dichromate and with concentrated sulfuric acid to deduce the IUPAC name. So sometimes to do this, it is easier to sketch it out. So we've got a H there, and then an OH, and a CH3 at the end. Okay, we've got 2 groups. I'm going to let the alcohol take priority. So this is our longest chain, which is bute, so we know it's butan 2-ol. Then we've got this methyl group up here, which is going to be on the 3rd carbon. So it's 3-methyl butan, 2-ol. Draw the structure of the organic product B formed when A is oxidised in the reaction with acidified potassium dichromate. Well, from sketching the structure out at the top, I can see it's a secondary alcohol, so I know it's going to form a ketone. And that's going to be on the same carbon as the OH. Two isomeric alkenes, C and D, are formed when A, so we're going back to the structure at the top, is dehydrated in the reaction with concentrated sulfuric acid. Name the mechanism for this dehydration. Well, if we're dehydrating it, we're losing water, so we're eliminating something from the molecule. So it's an elimination. Draw the structure of each isomer. Okay, so when this is removed, it can either take one of these hydrogens or one of these hydrogens, and depending on which side it is going to depend where the double bond is. So that is one option, and this would be the other option. So this time I'm leaving that one in, and the double bond is going to be here. Name the type of structural isomerism shown by C and D. Well, the double bond is in a different position, so it's going to be position isomerism. List alcohol A, product B and isomer C in order of increasing boiling point. Okay, if we look at the three structures, we notice A has an OH, which is going to allow it to hydrogen bond. This has got a carbonyl group on it, which has got a strong difference in electronegativity between the carbon and the oxygen, so that's going to be dipole-dipole. Whereas this is just an alkene, so we're going to be looking at van der Waals. We're listing them in increasing boiling point, so the lowest boiling point is going to be the weakest force, which is the van der Waals in C. Next it's going to be the dipole-dipole, and the strongest, which would have the highest boiling point, would be A with the hydrogen bonding. Draw the structure of the isomer of A that is not oxidised by acidified potassium dichromate. So we know that tertiary alcohols aren't oxidised easily, so we want to draw the structure of the tertiary alcohol. So a suitable structure would be this one. And you can see the alcohol group is attached to a carbon, which is directly bonded to 3 other carbons. Draw the structure of the isomer of A that cannot be dehydrated to form an alkene by the reaction with concentrated sulfuric acid. Well, if the alcohol is on a carbon adjacent to a carbon with no hydrogens, then you're not going to be able to get it to dehydrate. So if we put our alcohol on the end here, and then this carbon has got 3 CH3s on it, then there's no hydrogen for it to take on that carbon, so it can't be dehydrated easily. Figure 3 shows a simplified representation of the arrangement of some amino acids in a portion of a protein structure in the form of an alpha helix. Name the type of protein structure in figure 3. That one is the secondary structure. That one you just need to learn. Explain the origins of the interaction represented by the dotted lines in figure 3. So we're looking at this one and this one. They're half hydrogen bonds, half dipole-dipole bonds. So we know that the nitrogen-hydrogen, or both nitrogen and oxygen, are very electronegative. Oxygen's still going to have a lone pair of electrons. There's no reason it can't donate those to the hydrogen. So let's put that into words. Okay, so we've got nitrogen and oxygen are very electronegative for 1 mark. The C double bond O and the NH are polar, which results in the formation of a hydrogen bond between the oxygen and the hydrogen. You've just got to explain what a hydrogen bond is, in which the lone pair of electrons on the oxygen is strongly attracted to the delta positive hydrogen. The tripeptide shown in figure 4 is formed from the amino acid glycine, threonine and lysine. I apologise if I pronounce them wrong, I'm not great at pronouncing amino acids. And you can see the 3 structures in the diagram. Draw a separate circle around each of the asymmetric carbon atoms in the tripeptide in figure 4. So we're looking for chiral centres for this one. And if we have a look, see, this one here has got 4 different things attached to it. Because of the OH, this one here has also got 4 things attached to it. And this one here has. All of the others have either got 2 hydrogens or only effectively 3 things. If it's got a double bond, it's effectively only got 3 things around it. And there aren't any more. So it's just those 3. Next, we need to draw the zwitterion of glycine. So we're going to have H3N plus and then C double bond O, O minus. Draw the structure of the species formed when the glycine reacts with an excess of bromomethane. Okay, so we know that the nitrogen on the glycine molecule is going to act as a nucleophile and it's going to swap places with the bromine. So what you're going to end up with is the original molecule of glycine, and in place of its hydrogens we're going to get the methane from the bromomethane all the way around. Now it says an excess, so it's going to go until there's no lone pairs left on the nitrogen, which leaves the nitrogen with a positive charge. We've got to balance that charge, and there's going to be a bromide ion associated with it. Deduce the IUPAC name of threonine. So threonine. Okay, so if we have a look at the structure of threonine, let's just draw it down here so we can see. Okay, now we've got the structure, we can have a go at naming it. So we're going to look for the longest chain. So we've got that as the longest chain. So we know it's going to be butanoic acid. Okay, then we can see what else is there. So we've got our amino group there, and we've got an OH group there. So we've got an amino group and a hydroxy group. You've got to use alphabetical order for these. So the amino group is going to go first. And the amino group is on 1, 2 on the second carbon. So we've got 2 amino, then 1, 2, 3 hydroxy, butanoic acid. Draw the structure of the species formed by lysine at low pH. So that's when it's in an acidic pH. So it's going to be a proton acceptor. So we need to have a look at where it could accept protons, and here's lysine drawn. So the nitrogen there could accept a proton, and the nitrogen there could accept a proton. So let's draw out the structure. So we've got NH3 plus on the end, and the carbon, then the carboxylic acid group, which will be intact because it's at low pH. Then we've got our CH2 times 4. Then we've got another amino group there, so that's going to become NH3 plus as well. Repeating units of two polymers P and Q are shown in figure 5. Draw the structure of the monomer used to form polymer P. Name the type of polymerization. So if we have a look at P, P looks like it's formed from an alkene, so that's addition polymerization. So let's put that in first. And then if this is our repeating unit, that's where the double bond was originally that will have broken. So we put that back in. And then what's around that at the moment stays there. And that's going to be the structure of the alkene that it was formed from. Draw the structures of the two compounds that reacted together to form polymer Q. So polymer Q is a condensation polymer. It's going to have been formed from a diol and from a dicarboxylic acid. So there are our two things. We've just got to put the OH's back. And the other one's going to be a carboxylic acid. Just drawing it here so I can see everything on the page at the same time. See, if it was an exam situation, you need to make sure you put structure 1 where it says compound 1 and the same for compound 2. Suggest an environmental advantage of polymer Q over polymer P and justify your answer. Well, polymer Q is a condensation polymer, which means it can be broken down easily. So if it's put into landfill, it will break down. It's biodegradable. So the advantage is Q is biodegradable. And we've got to justify the answer. So we need to say why it's biodegradable. So the polar C double bond O group, or we could say this is the delta positive carbon in Q and not P, therefore can be attacked by nucleophiles. And that leads to breakdown. Now that's enough to get you the mark. So you get 1 for that, 1 for that, and 1 for that. But you could say it undergoes hydrolysis as well, and that's another way it breaks down. That's still a nucleophile that would be attacking it. The anti-cancer drug cisplatin operates by reacting with guanine in DNA. Figure 6 shows a small part of a single strand of DNA. Some lone pairs are shown. The DNA chain continues with bonds at X and Y. State the name of the sugar molecule that is attached to the bond at X. Okay, the bond at X is, so we're looking at this. If you look on your in your data book, which it's shown in your data book, it gives it the name 2-deoxyribose. I don't know how strict they're going to be about the name, whether they're going to require the 2 or not in the exam. That's how it is in the mark scheme, and that's all we've got to go by at the moment. Messenger RNA is synthesised in cells in order to transfer information from DNA. The bases in one strand of DNA pair up with the bases used to synthesise RNA. Fig 7 shows 2 bases used in RNA. Suggest which of the bases, A and B, forms a pair with guanine. In Figure 6, when messenger RNA is synthesised, explain how the base that you have chosen forms a base pair with guanine. So the answer is base A. And the reason for that is it looks like it's cysteine. So we've got this being guanine, and this is base A. And you can see that the top NH forms a hydrogen bond with the O of guanine. You've then got the nitrogen with the lone pair forming a hydrogen bond to the NH, and you've got the oxygen with a lone pair forming a hydrogen bond. Now, in the mark scheme, you can write the answer to this out, but there is nothing to stop you drawing this. You've got the structures on your data book, and it might be easier to draw it and state that they are hydrogen bonds, because that would get you full marks. But if you want to write the answer, this is what it would look like. Cisplatin works because one of the atoms on guanine can form a coordinate bond with platinum replacing one of the ammonia or chlorine ligands. Another atom on another guanine can also form a coordinate bond with the same platinum by replacing another ligand. On figure 6, page 12, draw a ring around the atom in guanine that is likely to bond to platinum. So I've copied the image in here. These are involved in hydrogen bonds, so they're not going to be available. So the only two left with lone pairs are going to be this one or this one. If you've circled either of those, then that is the correct answer. An adverse effect of cisplatin is that it also prevents normal healthy cells from replicating. Suggest one way in which cisplatin can be administered so that these side effects are minimised. So there's two things you could do. Use in very small amounts, or you could target the application to the tumour. Diaminobenzene is a very important intermediate in the production of polymers such as Kevlar and also polyurethanes used in making foam seating. A possible synthesis of 1,4-diaminobenzene from phenylamine is shown below. A suitable reagent for step 1 is ethanoyl chloride. Name and draw a mechanism for the reaction in step 1. So let's see what's happening in step 1. So we've got ethanoyl chloride, and it's going to be attacked by the nitrogen, which will have a lone pair. Now you can see going from step 1 to step 2 that the nitrogen, hydrogen, benzene rings stay intact. So they're not taking part in the reaction. So don't look at benzene mechanisms. That's not going to be one of those. This is all to do with the nitrogen swapping places with the chlorine. So those electrons are going to come in to carbon. Those electrons are going to move out to oxygen. So we've now got that pair of electrons from the bond on the oxygen and negative charge. Nitrogen's formed an extra bond that it didn't have before. And we've still got that chlorine. So we need to sort out all of these charges. So those electrons move back to form the double bond. That leaves, and then one of these bonds breaks in order to sort out the positive charge on the nitrogen. And then we've got the same structure as in the question. So we've added something and then taken something away. So it's addition elimination. We tend to call it nucleophilic addition elimination, but the nucleophilic bit isn't essential for the mark scheme. In terms of the marks for this, you obviously get 1 for the name. You get 1 mark for both arrows in that first stage. You get 1 mark for all 3 arrows in this bit. And you get 2 marks over here. So there's 1 each for those arrows. It's mark 1 and mark 2. Mark 3 is for those 3 arrows, and mark 4 is for the 3 arrows and a lone pair. Right, so it's the structure as well that they want over here. They also want an additional bit. They want this showing, which has never been essential in the past. They want that showing to show that it goes. That is optional. Checking the mark scheme. That second one is for the lone pair on the oxygen and then the structure. So that NH2 is optional, but that is how it would leave. It's also a bit of a hint if you're writing an overall equation as well, that you don't get HCl formed. In an experiment, starting with 5.05 grams of phenyl amine, 4.82 grams of purified product were obtained in step 1. Calculate the percentage yield in this reaction. Give your answer to the appropriate number of significant figures. Okay, so we're going to start out with working out the expected mass of the product. So we're starting with 5.05 grams of phenyl amine. So we want to work out the moles of phenyl amine. So it's going to be the mass over MR. The mass is 5.05 grams. The MR is 93. So that's 5.05 divided by 93. So it's 0.0543. Okay, that's going to be the same as the moles of the product. So the mass of the product you would expect is going to be moles times MR. And the MR of the product is 135. So that's 7.33 grams. Okay, they give you a mark for working that out, and they give you a mark for working out the MR of the product. Right, so I want the percentage yield. So this is the actual mass that you ended up with, divided by the theoretical mass, or the maximum theoretical mass, times 100. So that gives you 65.75% yield. Now we need to do to the right precision. So that's to 3 sig figs, that's to 3 sig figs. So our answer should be to 3 sig figs. So it's 65.8%. Just be really careful, because this give your answer to the appropriate number of significant figures seems to be cropping up a lot across the AS and the A-level papers. It's something you will lose a mark if you don't do it correctly. A reagent for step 2 is a mixture of concentrated nitric and concentrated sulfuric acid, which react together to form a reactive intermediate. Write an equation for the reaction of this intermediate in step 2. This is where reading the question really carefully comes into play. It's not asked you to write an equation for the reaction between nitric acid and sulfuric acid. It's asked you to show a reaction between... it's basically asked you to write an equation for step 2. So it's the nitronium ion reacting with the product of reaction 1. So this is what the nitronium ion is going to react with. There's our nitronium ion, which it's not asked us how we make it, it's just told us it's been made from nitric acid and concentrated sulfuric acid. So it's expecting you to know that that is the product, or that is the reactive intermediate. Okay, that is going to react with the benzene, and because it will be constrained, it's always going to go far away as possible from the existing group, so it's going to add on to the bottom. It's not asked us for a mechanism here, it's just asked us for the equation, and obviously we're going to have H plus left over. It's a benzene reaction, so it's going to be an electrophilic substitution. You've got off lightly, you've not had to draw the mechanism. And if you think you have got off lightly, because you haven't got to draw the mechanism, that might be something that's worth practicing. Suggest the type of reaction occurring in step 3. I've put step 3 at the side so you can see what's happening. So we've got this big group at the top turning into NNH2, so we're removing quite a lot there. And the way we're going to try and break the carboxylic acid off, so we're hydrolyzing it. Identify suitable reagents to use in step 4. So let's have a look at what step 4 is. So in step 4, we're going from an NO2 group to an NH2 group. So we're reducing it, and the best reagent to reduce nitronium to an amine group is tin and hydrochloric acid. Butanone is reduced in a two-step reaction using sodium borohydride followed by dilute hydrochloric acid. Write an overall equation for the reduction of butanone using an H in square brackets to represent the reductant. Okay, with these, it's sometimes easier to sketch it out at the side so you can see what's happening. Now I know when I reduce this, I'm going to break that double bond and I'm going to add a hydrogen on there and a hydrogen on there. That's going to make it much easier for me to write my final formula, because I've got CH3, CH2, CH, OH, CH3. It also shows me that I'm adding 2 hydrogens, so I can balance that equation easily. By writing out the mechanism of the reaction, explain why the product has no effect on plain polarised light. So we know we've got to put the mechanism in. So let's put that in first. Okay, so we've got the mechanism drawn. This is one of those questions where it's marked in levels. So level 1 is for 2 stages out of 3, or incomplete explanations. You'd get level 2, which is 3 to 4 marks. All stages are covered, but the explanation may be incomplete. And then we've got level 3, which is 5 to 6 marks, all stages covered and of the explanation, and it has to be communicated coherently and shows a logical progression. So let's have a look what we would need for each of the stages. So to get a full answer to stage 1, you want to say that it's a nucleophilic attack. On a planar carbonyl group. And that the H- attacks from either side, or you could say from above or below, and that's a perfect stage 1 answer. So for stage 2, you would show the product of step 1. You would say that the product exists in 2 chiral forms, and that can be stated or drawn, and it's a racemic mix. It was fine to say there was equal amounts of each enantiomer as well. That would be a complete answer for stage 2. For stage 3, you would say it's an optical isomers, rotate the plane of polarised light in opposite directions. And then you would say racemic mix, the effects cancel out. They're not nice ones to mark. I know certainly for my marking I will have been quite strict on that. I think Wendy's has been a little bit more generous. We can only hope the examiners will be generous on these sort of questions. But just make sure you have got a logical order that follows through and you annotate it. Diagrams are always going to be worthwhile putting in. A peptide is hydrolyzed to form a solution containing a mixture of amino acids. This mixture is analysed by silica gel thin layered chromatography. using a toxic solvent. The amino acids are identified from their RF values. Part of the practical procedure is given below. Wearing plastic gloves to hold the TLC plate, draw a pencil line 1.5 centimetres from the bottom of the plate. Use a capillary tube to apply a very small amount of the solution of the amino acid to the midpoint of the pencil line. Allow the spot to dry completely. In the developing tank, add the developing solvent to a depth of not more than 1 centimetre cubed. Place your TLC plate in the developing tank. Allow the developing solvent to rise up the plate to the top. Remove the plate and quickly mark the position of the solvent front with a pencil. Allow the plate to dry in a fume cupboard. Parts of the procedure are in bold text. For each of these parts, consider whether it is essential and justify your answer. Okay, 4 marks, 4 pieces of bold writing. So the first one is wearing gloves. So we can put gloves. They are essential for 2 reasons. There are amino acids in your fingers that will transfer. Also, you're handling a toxic solvent. And you don't want that on your skin. So you would want to make sure that you had gloves on for that too. The second one, the depth of 1 centimetre. Well, that's going to be essential because you need it to it must be below the pencil line. To avoid washing off the amino acids into the solvent. Okay, the next one is allow the solvent to get to the top. It's not essential, it needs to be near the top. So within 1 centimetre of the top. The longer you leave it to go, the easier it is going to be to measure it. So as long as it's within 1 centimetre, that's fine. So I'd say that one is not essential. The last one, dry in a fume cupboard. That's essential, the solvent's toxic. You don't want to be breathing it in. This last question says, outline the steps needed to locate the positions of the amino acid on the TLC plate to determine their RF values. Now, I would be very tempted for this to sketch out the TLC plate. That's a particularly bad drawing. So the first thing you're going to need to do is to develop it in such a way you can see the spots. When we did this, we sprayed it with ninhydrin, so you need a developing agent. Sometimes called a locating agent, to see the spot. Okay, you then need to measure this value here. And you need to measure this value here. And I'm going to label these. So then I would say that the RF value is the distance travelled by sample. Put A there. Divided by the distance travelled by the solvent. And that's going to get the rest of the marks. Outline the steps. You could go through the fact that you are measuring those, but I think that diagram would be sufficient to explain what's happening.